to, as Richard has said, the third colloquium in this winter term. And you can tell from the 25 minutes we spent setting up the computer that today's talk is about supercomputing and about trying to understand the universe with the help of computers. I hope you do better than we do. So it is a special honor to have Simon Portegies Zwart as speaker. Simon is professor at the Sterrewacht Leiden, at Leiden Observatory. Before that, he has been in Amsterdam, where he obtained his where did you get your PhD? Amsterdam, right? Oh, in Utrecht. In Utrecht. You need to update your CV. Is it so? Yeah. Okay, so he got his PhD in Utrecht. Then he went to the Planetary Institute in Amsterdam as Spinoza Fellow. Then he went to the other side, almost of the globe, to the University of Tokyo as KSPS Fellow. From that, he got the Hubble Fellowship, which he took to MIT, Boston University. Then he came back to the Netherlands, to Amsterdam, where he first was a Knapp Fellow and then assistant professor before he then moved to the Sterrewacht Leiden. He has received a number of very nice and prestigious prizes, such as the Hubble Fellowship or the JSPS Fellowship, but also the Caspar Schmalz Prize of the Dutch Astronomical Society, the Wim Nieuwenhof Prize, because he does supercomputing and he is very good in that. He also got the Gordon Bell Prize. He was nominated. Yes, nominated. Yes, but you got this prize for the fastest computation.
Yes.
It's true, right?
Yeah.
Yes. So, and today we will learn more about how the sun lost its family. So the question of how can we try to employ stellar dynamics and star formation to trace back essentially the birth environment of our own solar system. So again, thanks for your patience, and let's welcome Simon.
Thanks, Rolf. And interesting technological difficulties, which I haven't experienced for a decade, I think. So maybe this is sort of a post-corona sort of regrowth into technology and how to give live talks. But the operation between microcomputers and beamers replaced backup rooms is maybe a challenge for these things. But if it's working just with supercomputers, once it's working, they work pretty fine. It's very often how to get them to work, which is the difficulty. So this is a topic on the lost family of the sun I have been talking about for maybe for the last decade. It was about a decade ago that I was thinking about it, writing a little article for Scientific American, and the editor kept saying, you should say something about the sun. You should say something about the sun. But I wasn't interested in the sun because it's just a single star in the galaxy. Who cares about single stars? Anybody cares about single stars here? No, right. But so in the end, I thought maybe the sun wasn't always single. Maybe the sun was born in a cluster. And therefore, I came the idea of the family of the sun. And the question, can you find the family back? Or what are the consequences of being born in a family? Now, we all know, I hope at least that we all know what the consequences are to be born in a family. But it also means that there's a lot of turmoil going on. There's a lot going on in the family. And it's the family of the sun that I would like to share some thoughts about. So everything that I say is complete faith. It's all computations. There is no real observations and only real data from real computers being processed in a way and making an interpretation for the scientific content. So everything has to do with the sun's family. And I think that the sun, if you think about it, born in an environment which has some similarity to what you see here. Right? There are stars, there is gas around, the gas forms stars, there is an interaction between each of these things, but eventually the star cluster will dissolve and drift apart. So, if you ask a young kid to draw the solar system, they will do something like this: a star, planets, maybe some comets, maybe some stars in the background. But in total, it's sort of a rather organized system. And the organization of the solar system is also what makes it such standing out compared to other systems and to what we think it could have been. It could have been a big mess. Now, if you summarize sort of the main questions you would ask about the solar system, which are hard to explain, which is, for example, the sun is an isolated star, where all stars that we know of are born in clusters. On the other side, many stars in the galaxy are isolated and are single, so maybe it shouldn't be a big surprise. The planets are in almost circular orbits up to about 45 AU. So at some point, the solar system really rather suddenly stops existing almost. Right? There are no planets outside 45 AU or outside 30 AU. And there are basically no asteroids also outside that region, which we call the Kuiper cliff. So that is the region beyond 45 AU. The disk suddenly stops. So the debris disk of the solar system suddenly stops. Now, if you look at disks in the galaxy, which are observed now in plenty, they're very often bigger than this 45 or 30, 45 AU. And you could wonder, why is that the case? Why are some disks smaller, but why are, in particular, the solar system disks so small? Further out, we get a dense populated Oort cloud. So the Oort cloud also is sort of, well, of course, a big cloud of big in size. It extends almost up to the next star, to 200 AU. But it's also populated with something like 10 to 14 asteroids or comets or proton comets, whatever you want to call them. Never observed really directly, but anticipated by Oort in the 50s. Then there is several things that make the solar system stand out from a chemical or reaction point of view. For example, there is multiple heating events in the very early solar system. Heating events that cannot readily be explained by sort of the early formation of the star. There is a tilt of the ecliptic with respect to the equatorial plane axis of the sun. So why is the sun tilted with respect to the plane of the planets? There is an overabundance of aluminum in the short-lived radionuclides in calcium-aluminum inclusions. It's also originating from the early solar system. And there is an unusually low abundance of iron, which normally iron and aluminum sort of come in the same proposition from, for example, supernovae or Wolf-Rayet stars. So these are a number of questions I have about the solar system, and these questions are related to sort of the story I'm going to tell. And the story is about star formation, planet interaction, disks, and in the end, the solar system and the consequence for the solar system. And as I said before, everything is done in computers, everything is a simulation. I try to make the connection with the observations, of course, not only for the solar system, but also for other parts where we can test that. But in the end, it's so there will be a number of animations, and that was one of the reasons why I had so difficulty. We have to connect my computer because then we can do the animations embedded, if it works. We'll see. Now, the classic picture, we just had a talk by Martijn in one of the group meetings, and Martijn showed basically the same picture. If you look at star formation, people tend to show this picture. And one thing that I always find curious is, why do we spend 4 of these images to the region of a time which only takes 10 million years, and part that takes billions of years to go to the picture? There is sort of a temporal discrepancy in this picture. But maybe that shows the preference of the person who made this picture. The other thing is, I don't know of any stars. Let's try this. Maybe on the side. This is the sun, and this is the planet. Okay, good. So why this? So this part takes 10 million years or so, maybe a bit longer. With this part, this part takes at least for the solar system 4.5 billion years or so, right? But the other discrepancy is, this is a single star. Well, this cloud probably is more massive than the mass of a single star, 2 stars, or 5 stars. But it may be maybe 10,000 solar masses or so. So what we think is that this branch somewhere should split off into 1,000 stars, and you make 1,000 types of objects like this. Now, these objects interact because they're born in a bound or semi-bound environment where there is gas around, or stars around, or planets forming. It is a mess. And the observers completely agree, I think, that it is a mess, and that's why we have all these big telescopes looking at these regions. But the theorists sort of tend to be stuck into this sort of idealized picture where things are clean and nice and pretty as we like it in the computer. But in reality, it is also a mess. So in order to resolve that mess, you have to put all the physics in, you have to put all the different processes, treat them in the proper ways, and then have a big enough computer optimized it enough that you can really do the calculation. Now, I will show you a few of the efforts we are doing into that direction. I don't want to say that we have a consistent picture of this whole process, but at least we are on the way of trying to understand each of these ingredients. Now, this I do not alone. There's a lot of people involved. Some of these people you may recognize. Actually, the professor in this team, I want to make completely black, so you wouldn't even see them, because these are just the steering people. But the most important people are the grad students, which are here in orange. And they are, of course, all wanting for a job as a postdoc. Then there are the postdocs, which are in blue, which are also wanting for tenure track positions. And then there are the people who left the field, and most of them are now making software for selling stuff, or making software for doing machine learning. Most of them are really experts in machine learning by now. So this is definitely not a one-man project. This is a whole team effort, and it wouldn't be able to do it otherwise. And it's all based on the Muse. The Muse is a software environment Steve and Bill and I started developing like a decade ago. And we realized that universes, so the theories were a little bit behind in the observers in that case. We realized suddenly that actually you needed multiple physics in order to address all the physical problems we have, and all the things that observers see in order to interpret them. You need sort of multi-physics. So I will not name any codes apart from saying it's a Muse, and maybe once in a while, certainly if there are questions, of course, there are different types of codes combined together into an environment. And this is a book Steve and I wrote about it. This was published in 2018, and next year we hope, at least we expect, the new version of the book will come out. Now, this is a molecular cloud collapse simulation, and this is one of those calculations done by Sean Lewis of a molecular cloud done using a Muse of how star clusters form. So this is really the first step in the process from our perspective. You have a molecular cloud. Molecular cloud has some sort of temperature profile, density profile. It collapses. The stars are formed on the little stuff you see here. And what you see here is you blow out of the stars of the gas. And in the end, it's a supernova, and the star explodes, most massive star explodes, blowing away all the gas basically out of the early star-forming environment. This is sort of the type of cluster we think the sun was formed. So the sun was formed in sort of a clustered environment where stars interact. Now, a number of things are important here. One of them is that it's gas and star, so it's sort of a mix of stuff that gives all kinds of interesting processes. Stars are evolving, but you wouldn't see much here except maybe for the supernova in the end of the animation. And the other thing is the stars move around quite busily. They're not formed in sort of a plumber type sphere that people think about when you think about star clusters, but it's frothy, it's sort of chaotic, it's a fractal distribution of stars in space and velocity. And that is what makes for a very interesting environment to study, and also from a further perspective. You can wonder, what are the consequences of being born in such an environment? If, for example, you are a nice isolated planetary system with a disk maybe extended for something like 100 AU. So here you have sort of this protoplanetary disk around a star, or sort of stellar disk at least, is three projections. Here is on the side, on two sides, and here's from the top seen. And this disk is 100 AU at this moment. So this is disk born at something like 100 AU. And then it will evolve in time. If it evolves in isolation, it will start making planets, it will dissolve, the gas will be blown out, dust will be created, and then at some point you will have a planetary system. But in a star cluster, something different may happen, because the disk is perturbed in all kinds of ways from the rest of the star clusters. So you can measure that, for example, in the evolution of the radius of the disk. If you look at the function of time, so this star, this is not the sun, but this is some star in one of our simulations, a number of stars in one of our simulations, actually the simulation where Martijn Wilhelm, which was born at an age of 1.5 million years. T is 0 for us here is when we sort of start the calculation. You see the disk sort of grow in time. This is side from the disk grow in time, and then you get truncated. And then they evolve further, some get truncated a little bit more, some grow back in size, and then they get truncated again. And the truncations have two different possibilities. One is stars meet each other very closely, perturbing each other's disks. And the other is that a supernova or a stellar wind comes by, a massive star comes by, and photo evaporates the disk of its companion. There are multiple processes operating at the same time. And one of the things that Martijn tried to find out is what is actually the dominant process. We have a big fight on that, and I think it's a different process than he thinks. Maybe in the end he will be right. So he thinks that the photo evaporation is way more important than the truncation of the passing star. And that seems to be the case, except if you then take intra-cluster gas into account, things again gets a little bit more complicated. Now I'll get to that in a second. So one of the things that you see there is here you see a few stars with this inside the star cluster. How do they evolve in the star cluster? And have here the core radius and the half-mass radius. And this of course started as a faulty type of cluster, like the ones we made in the simulation, previous animation. But in the end, it's easy for a theorist to talk about half-mass radius, tidal radii, and core radii, or to get some structure on your star cluster. Now, the star is, for example, born here. You see the size of the line is proportional to the size of the disk around the star. It's born with a certain size. The disk grows a little bit in size due to the viscous growth of the disk. And then something happened around here. You see it's either an encounter or it is a massive star that passes by the disk, photo evaporating part of the disk, and the disk gets skinnier. It gets less massive, it loses mass, and it shrinks in size. And some stars lose their disk very quickly. This star evolves from this position to here and loses its disk with the red cross, and then simply it continues diskless. There's a single star without a disk. It probably never will get any planets. But this star has the possibility of growing planets in this sort of reduced disk. The consequence is that these planets are always formed either not at all, because the disk is gone because of the interaction with the neighboring stars, or in a perturbed disks. So the idea of star formation in isolated disks will not happen in a star cluster, even if the star is relatively far out from the cluster, like in this case. Even there, you destroy this easily, or you perturb them, or they get warped, or if material is exchanged from one disk to the other. Now you can test this, of course, because one of the predictions from this calculation would be that stars in the center of your cluster are more perturbed, or more easily perturbed than stars on the outside. Now, in the computer, you can very easily see that, and you can compare it with observations, that we do in this picture. It was part of the PhD thesis of Sterrewacht. You see here a simulation result, which is the probability, the mean disk mass, the mean disk mass, let's say, as a function of the density of your cluster. If you have a dense cluster, disks are easily perturbed, like you have here. So there's a dense cluster that before stars per cubic parsec will have smaller disks or lower mass disks on average. And lower density clusters, let's say 10 solar masses per cubic parsec, 10 stars per cubic parsec, will have on average more massive disks in the end. And on top of that, we have a number of observations of star clusters like Taurus, Lupus region, the Orion Nebula cluster, and what is sort of the typical size of these clusters. So it seems to, I mean, we don't want to claim that this is the right answer. It's just that the trend you see in the simulations, denser environments have smaller disks or lower mass disks, seems to perpetuate in the observations as well as in the simulation. So we seem to understand something of this process and how it's going on. Now, what happens in such a star cluster is that the disk is perturbed by several processes. So one of them is the wind. What you see here, the truncation of the disk is caused by the massive wind of a star that plows into this star called disk. So here you have the disk and the star, and the star is somewhere in the middle. The disk is orbited around it. It's seeing edge on, but we initially put it onto a little angle. And what comes here is the wind of the star, in this case, of a supernova blast wave that blasts the disk of that star into pieces. So that disk is destroyed almost, it's reduced in size, the initial picture, to the final picture by about a factor 2. So the wind of the supernova blast wave reduced the size of the disk. Now you can quantize that. In this animation, if you don't do that with one disk, but with a lot of disks in your simulation, you start with sort of a frothy calculation, like you see on the top right. And the star cluster, all the stars are moving with respect to each other. The winds are blowing, the stars are truncating each other. What becomes the size distribution of the disk eventually, if all stars start with the same disk, Then in the end, you sort of follow this observed red dotted line distribution of disk cycles. So let me show that again, because it's basically two animations. One is the projection of the cluster, and the other is the disk size distribution of the things. So this is the movie of how the disks are destroyed by, in this case, supernova or stellar wind. And this is how they are destroyed by encounters and maybe other processes. In the end, you think you understand something of the distribution of sizes of disks based on the fact that they are being perturbed by other stars in the neighborhood. Now, if you look at multiple of these simulations, like how are these disks destroyed, then there is a degeneracy in the answer. For example, what you see here is the solar system disk. This is the debris disk, blue line, dark blue line, the debris disk of the solar system. In surface density versus distance in log units. So these are the planet and the Trojan, the asteroid belt, the Trojans, Jupiter, Uranus, Neptune, Trojans, and then there's the Kuiper cliff. Here's the Kuiper belt, and here's the Kuiper cliff. And what you see is the initial density distribution of the disk assumed in this calculation. And after a certain interaction, in this case, is a supernova, at the distance of 0.1 parsec at an angle of the distance of 60 degrees, or at the distance of 0.4 parsec at the distance of an angle of 50 degrees. So an edge on disk is, sorry, the normal phase on disk is much easier to perturb than an edge on disk. And that's what you see here in the degeneracy of these solutions. So you can have multiple distances or angle of the disk are degenerate in how strong is the effect of the supernova blast wave onto this circumstellar disk. It makes life a bit more difficult, but of course you can do grid of calculations where you vary the distance to the supernova or you vary angle of the disk and then see how big does the disk get. So what distance is the disk perturbed or destroyed in order to compare it with the solar system, for example. Now you can do that here. We have the distance of to the supernova from 0.15 parsec to half a parsec. And the disk angle, and this is phase on, and here it is edge on. So the stable disks are on top here, and the fragile disks, basically the edge on, the phase on disks that are easy to destroy by wind, are on the bottom here. And the solar system, if you want to explain that here, you would like to truncate between something like 30 and 45 AU, right? I mean, that's sort of the size of the disk at the moment. So you would expect that if a supernova happens in the neighborhood of the sun, it should have happened between something like, probably between 0.3 and 0.6 or so parsec. If it was on edge on, the supernova, and if it's phase on, it can be as close as 0.15 parsec, right? It can be very close. So this is sort of the region where a supernova near the sun, which is the very natural consequence of the sun being more in a star cluster or sufficiently less a star cluster, disturbing the circumstellar disk of the solar system. Now you can plot that. Here's the allotted region, so to say. This is distance again versus angle, and this is certainly the allotted region. And on the bottom here, color coding here is the temperature, to which temperature this disk is being beaten by the supernova. So what happens is if a supernova goes off nearby, you have a beautiful fireworks on the sky, and a few hundred years later, this nuclear blast wave destroys your circumstellar disk. So that's sort of what happens here. And the shaded region here is the area where this is consistent with sort of the size scale of the solar system. And there is another effect if you look at the same movie, and that is that the disk is sort of tilting in the wind. It's like a sailing ship, right? So if the blast wave of the supernova or the blast wave of the Wolf-Rayet wind, the initial disk was on an angle of 45 degrees in this case, but due to the supernova, the disk is sort of moving in size, moving in direction. And the reason is that the disk is probably accreting zero angular momentum material or low angular momentum material, and that causes the orientation of the disk to change. Now that is an interesting thing. So that may be related to the fact that the circumstellar disk at the moment, and the debris disk we have, the planetary disk, Ecliptic, has an angle with respect to the equatorial plane of the sun of about 7 degrees. So can we explain the 7 degrees? And then here you see an example where we have the distance to the sun. The dots give the ecliptic plane of the solar system. And the yellow curve here gives you the final result of one of the calculations of how a disk is perturbed due to a blast wave of a Wolf-Rayet wind or supernova. So it may well be that the disk of the sun has been having a little kick, not only truncating the disk, but also pushing it sort of out of the plane, out of the equatorial plane of the sun, just before the planets were formed. And at least so now you can search for what sort of parameters, how far does the supernova have to be, or at what angle does the disk has to be before the supernova goes off. And you can do the same plane. So here you see the same plane, this to the supernova or Wolf-Rayet star, and the angle between phase on and edge on of the disk. And then you see that this is the degenerate function. And by doing the 45 degrees in the movie, I sort of had the most effective tilting of the disk, which is not completely surprising, of course. So at the largest distance of about 0.4 parsec, at an angle of 45 degrees, you can tilt this to an angle of about 7 degrees, which is the angle observed of the ecliptic with respect to the equatorial plane of the sun. And the observed angle is between 4.4 and 6.8 degrees. And that happens in this sort of greater than shaded area. Now, if I overlap these areas, I'll have the truncation of the disk, I have the tilting of the disk. So this regime, what remains over, is the regime where you truncate and tilt the disk due to the presence of other stars in the protosolar cluster. You see it magnified here. And I would like to see, okay, if you have this disk and it is loaded with aluminum and iron and the burning processes of the post-supernova or of a Wolf-Rayet wind, how does the disk then accept this material? Does it really accrete this material? That you see here in the color coding on top of this allotted region, of most optimum region, to have the sun in this perturbed environment. And then you see that the enrichment due to, for example, supernova, you take an example, supernova in this case, you enrich it to something like 10 to the minus 8, 10 to the minus 9, maybe 10 to the minus 10. You don't enrich the solar system so much by this material of the supernova blast wave. And the reason is that this circumstellar disk is like a brick wall through which you throw ping pong balls. So the supernova blast wave is very dilute, it's extremely hot, and it's throwing ping pong balls at a brick wall. No ping pong ball will stick to the wall, right? Because they just bounce off. So all this material that is accreted by the disk actually may reduce the angular momentum of the disk, but the material doesn't really stick to the disk. And you cannot enrich the solar system sufficiently to explain the amount of aluminum 26 in the early solar system. Therefore, you need a slower wind, and therefore you need the Wolf-Rayet wind. So the Wolf-Rayet winds may be able to accrete the high aluminum rich material, and the supernova cannot do that anymore. And that's why we have an overabundance of aluminum and an underabundance of iron in the solar system today. And maybe we are truncated and at the same time tilted by about 7 degrees with respect to the solar equatorial plane. Now, if you know how this works for one example or number of examples, of course, you can run in a body code where you put all these processes in, and then you search for which type of parameters of my cluster, let's say the size of my cluster in parsec, first the number of stars, where do I have the most probable region to make a solar system-like object. And it turns out to be at a radius of about 0.7 parsec and about 2,000 or 3,000 stars. So based on these results, I think that the sun was formed in a star cluster of about 3,000 stars and a size of about 0.7 parsec. Now that happens to be sort of the average cluster. All clusters around us sort of have this type of parameter or in this machine. So it was not a very massive cluster, because in that case, we would have too many supernova, the whole planetary system would be destroyed, there will be encounters, and we would not have any planets. We wouldn't be there. But if we have sort of in this ballpark machine of a parsec and a few thousand stars, we have the optimum area of parameter space to be born in. So I think we are born in a cluster of a few thousand stars at about a parsec distance. Now, if it's 0.7 parsec or 1 parsec, I don't care. It's sort of order of magnitude parsec, right? So the interim conclusion is just what I said. In order to explain the truncation at 45 or so AU, to explain the tilt of something like 7 degrees, to explain the enrichment of aluminum with the coordinates of iron, we would be born in a cluster of about 3,000 stars with the size of about a parsec. And in such a cluster, about 10 supernova would go off. So I only needed one really to explain this phenomena, but 10 in total go off, and each of them would perturb the solar system differently. It would be nice to see sort of what is the consequence of each thing. You do need to evolve a star before the supernova in order to explain the aluminum enrichment. Now, so far so good, right? This was a protoplanetary disk. This was a disk of gas and dust, and it is very smooth. And such a disk is like a taiko drum, right? You drum it, and it basically is silent immediately. It moves a little bit, it makes some noise, but then it sort of is quiet. But really, after the protoplanetary disk turns into planets, the disk is much more fragile, and it's much more like one of these glass harp instruments. If you touch one of these glasses, the whole instrument basically will start vibrating. So once the circumstellar disk turns into the pre-disk and the planetesimal disk, then it gets very fragile for any encounter. So where we had a very stable disk in the early phase, we have a very fragile disk after about, 10 million years or so. So the question, of course, is what for consequences are there? If the star cluster deprived of its gas, and the stars are having planets, and the stars are moving around, evolving, exploding, bumping into each other, and that will have profound consequences for the evolution of the planetary system. And the moment you have a planetary system, something else interesting is happening. That's exactly what happens in these glass harps. The moment you touch the outermost planet of your planetary system, the perturbation of that planet will propagate to the inner planets. And everything will start vibrating. All the planets will start being affected by the fact that you just touched this outermost planet. Because planetary systems are formed in sort of a restless equilibrium, which causes the propagation of these perturbations throughout the entire system. So let's have a look at the consequences of that. First of all, you can make a picture where you see if a star with a protoplanetary disk, or not with a protoplanetary, it's a debris disk, is perturbed by a passing other star. Where are the stars being perturbed? Where are the asteroids that you are perturbed ending up? What sort of orbits? And Suzanne also made this nice picture where you take the star with a disk around it, with some planets on the inside, and this is the 200 by 200 radius disk. It's perturbed by another star passing by, and you see that the asteroids in the blue region all end up in relatively low inclination and low eccentricity orbit. But the ones in the red region, they end up in a much broader distribution of inclination and a much higher eccentricity distribution. So where you are born in the circumstellar disk as a planet or as an asteroid is very sensitive to where you end up after an encounter with another star. So you can do sort of planetary system archaeology. You can look at your planetary system and say, hey, I have a very high inclination and I have a very high eccentricity. I was probably born in either the yellow part or I was born in the brown part. So you're born in this yellow part, here, it's very small area here, or in the brown part, it's sort of distributed over the disk, right? So this is all basically three-body dynamics, right? I mean, the asteroids hardly feel each other. Okay, planets feel each other, of course, but the star and the asteroid and the other star passing by, it's a three-body problem in principle, and that means that you can really derive these equations quite nicely. That's a restricted three-body problem. Now, and the perturbation you give, if you have an encounter of a star with a planet and another star passing by, the perturbation in eccentricity, for example, and delta eccentricity, so the eccentricity you achieve after an encounter depends on the eccentricity you already have. The encounters will always move you along this line, where its eccentricity is high, your delta in eccentricity is also high. And if your eccentricity is small, your change in your eccentricity is also small. But if you are internally resonating into the planetary system, you follow these more pointy curves where you have conservation of angular momentum. So internally in the planetary system, you can have huge variations in the change of your eccentricity depending on your eccentricity. So the behavior of an encounter from outside is completely different in a planetary system than the perturbation inside the planetary system. So not only can you disentangle the consequence of an encounter onto a planetary system due to another star, you can also disentangle the consequences of the internal perturbations inside the planetary system, simply by the dynamics, basically Newton, what's happening here. And it helps you to understand how these planetary systems form. So if you start a simulation with a star cluster of say 2000 stars with 1 parsec period radius, and you give all the stars 3, 5, 4, 5, or 6 planets, like here in the dashed histogram, after 10 million years, you'll see that there are still stars which never had a serious encounter, nothing really perturbing happened to them, but the number of them have lost their planets, or at least a part of their planets, and they have become reduced planetary systems. So the planetary systems which have 5 stars tend to be reduced to one or two planetary systems. And you see that doesn't happen for all, but it happens for about, maybe a quarter of the planetary systems. So a quarter of the planetary systems in a star cluster of about a few thousand stars, with a typical period radius of 1 parsec, will be dynamically affected by being born in a star cluster, simply by being there. And this is still independent of the fact that the circumstellar disk, before the planetary system was born, already may have been perturbed. Now, many of these planets are ejected from the cluster, or either promptly, the moment they get an encounter, they're immediately ejected from the cluster because they have a velocity way higher than the escape speed of the cluster, and then they become single, isolated, free-floating planets in the galaxy, or there is a delay. They stay in the cluster. So these ones, the majority, about 2/3, escapes immediately as a function of time. You see here how many planets are being escaping from one of these star cluster simulations. It's a few thousand stars and a few thousand planets. And for many of these planetary systems, the planets are dislodged from their star, but they hang around in the cluster. They don't escape so easily, because their speed at which they escape is the orbital speed around the star, and that's typically not even larger than the escape speed of the cluster. So they hang around until they get a little push from a star, dribble over the tidal boundary, and become part of sort of a tidal tail of the cluster in the galactic potential. Now, Oumuamua, of course, is an interesting object that may be such a star, right? It may be such an asteroid that came by in the solar system in 2017. It was observed. This is the object. I like to call it the solar lapis, the lonely stone, but because a Klingon term was, you can't get published Klingon terms in scientific literature these days, but Latin terms is always very good. And what you see is the velocity of Oumuamua was about 30 kilometers per second. The velocity of horizon, with respect to the center of mass of the solar system, was about 55 kilometers per second. And if you compare that to young stars, then Oumuamua seems to indicate that it's a young object, and Borisov is indicated it's probably a rather old object, because it's more consistent with sort of an old population of stars in the potential of the galaxy. So the velocity distribution of stars you will explain here. So the debris that is lost from any protoplanetary system and becomes part of the galaxy, and they keep hovering around. And if you think about the solar system, there may be 10 to the 15 or 10 to the 16 asteroids in the solar system at birth, which was formed in the circumstellar disk. The majority of those have been ejected in sort of the galactic potential. So each star produces like 10 to the 15 objects. It's 1 star per cubic parsec. That means that you have a density of interstellar objects of 10 to the 14, 10 to the 15 asteroids per cubic parsec. And if you do that derivation for Borisov and Oumuamua, you also come to a density of about 10 to the 14 asteroids per cubic parsec. So the numbers are sort of consistent with each other. But of course, you have to remember that this is statistics on 2 objects, right? Not that that is a problem, because you can do statistics on 0 objects if necessary. Think about intelligent life in the universe. There are people doing statistics on this. Now, another thing that can happen is that one of these disk-watched asteroids, or planets, may be captured again by another star. And as you see here, the black dots here indicate in a number of our calculations, as the function of the distance to the star and the eccentricity, what sort of orbits do these captured objects require? Doesn't happen a lot. In a typical cluster of a few thousand stars with 1 parsec period radius. In this case, it happened like 6 times or so, 5 times. And the other ones are planets that were kicked out from inside the planetary system in very elongated orbits, probably by ejecting another planet. And the eccentricity of the planets that are ejected from the center of the planetary system, for the inner maybe 10 AU or so, must have very eccentric orbits, exactly as you see here in the red dots. But if you're captured, you can be captured in a relatively low eccentricity orbit. And that's why the eccentricity of the black dots is on average lower than that of the red dots. Now, example could be HD 106906, which is at a distance of 700 AU from central star, but we don't know its eccentricity. So the moment we know the eccentricity of this object and it's ever an almost linear orbit, then we say it's probably kicked out from the interplanetary system. But this has a relatively low eccentricity orbit, maybe 0.5 or so, and somewhere in this machine, we would say that maybe this object was captured. We only have to measure its eccentricity, which is not a trivial task. Now, an example in the solar system is Sedna. Here you see the solar system up to Pluto. And what you see here is the orbit of Sedna. So Sedna misses the solar system. So the asteroid Sedna can never have been ejected from the by planets into the current orbit because it never gets there. It doesn't reach there. It must have been captured from another star in a very early phase, very long time ago, when the sun was still part of a planetary of a star cluster, and in that star cluster, the sun either picked up another planet or an asteroid in this case, or it had an encounter with another star, and it was an exchange of asteroids. And Sedna was captured, was abducted from this other star. There is also astrologers working on Sedna, and they argue that if you're born with Sedna in the sky, in a certain constellation, you know, it's really bad because Napoleon was born with Sedna, and Hitler was born in the Sedna, and Putin was born in the Sedna, but you're all born on the Sedna because the orbit of Sedna is so large, with 11,000 years, that it's always in the same constellation. So we're all as bad as all these other people that are in that book. So don't buy it. Now here you see a simulation of an encounter between the sun and its protoplanet, its surface, the debris, and another star is in the debris, and see how they exchange their material. See how they exchange asteroids, and the sun captures asteroids. So the sun is the blue one. Sorry, the sun is the blue one. The sun captures asteroids from the red star, and you see they get in these orange elongated orbits, which are indicated here in simulated axis and eccentricity. And the diamonds in here are Sedna and its brothers and sisters in the same phase space. So you can reconstruct by looking at Sedna and family, what sort of encounter and what sort of other star, what sort of disk should it have in order to exchange material in such a way that you can explain the orbit of Sedna. And it turns out that it's relatively straightforward to do this. It's just a few body dynamic problem. You captured stars, you captured asteroids. Our own asteroid belt had truncated at 45 AU, exactly where we have the Kuiper belt, the Kuiper cliff. You get some scattered asteroids, which are the scattered, could be explained, scattered Kuiper belts. There are some unbound objects, which are tributes to objects like Oumuamua and other interstellar asteroids. But the nice thing is that the other star also steals asteroids from us. And we know in what sort of orbits they are, because we know in what sort of orbits his objects around us are. So since we know what asteroids are his, we can recognize our asteroids around him. And that means that we can go to this star and say, hey, these are our asteroids, we want them back, and you can have Sedna. Right? Now here you see a picture of how we do this. This is the constraining of the parameter space, and it means the scale goes on to many astronomical units. So the prediction is that there is a whole population of many objects, maybe 2,000, maybe even more, of asteroids in this regime of parameter space, at these inclinations and at these semi-major axes, going out to maybe 2,000, maybe 5,000 AU. We haven't seen them yet. So the second interim conclusion is the sun was born in a cluster of 3,000 stars. We already knew this, 1 parsec virial radius. The supernova happened. Sedna was captured from a passing star long time ago, and the encounter, they also have truncated the Kuiper belt. So keep in mind, right now we have 2 explanations why we have a truncated Kuiper belt. One is a supernova, and one is a passing star. I don't know which is one, right? It's not both, I think. But one of them is probably really doing the damage. And the dynamical truncation produces asteroids like interstellar asteroids like Oumuamua. Now, the last part, I would like to talk about Oort cloud. So I have been thinking a lot about the Oort cloud lately, and I have been at the moment that I sort of doubted about the existence of the Oort cloud. It's a very dangerous thing to say for a Leiden astronomer. But I didn't see any evidence. There are no observations. And you read Oort's paper, you think, yeah, this is rock solid, but you know, things have changed a little bit, maybe. So you read it again, and in the end, you convince yourself the Oort cloud, it must be there. There is absolutely no choice. But if the Oort cloud formed while the sun was still in its parent star cluster, it would be destroyed. We would have lost the Oort cloud because the Oort cloud is extremely fragile. If a star passes by in the star cluster, we would immediately lose half the Oort cloud. If two stars passes by within the Oort cloud, this distance, you're talking about 100,000 AU, right? That exceeds, that is quarter of a parsec, right? So stars moving around in this regime continuously in the star cluster. So we would easily lose the Oort cloud. So why do we have this Oort cloud at all? Now that is not a trivial matter, because the way you make the Oort clouds is, for example, by having planets. And we have the major planets, and the major planets are indicated as these curvy lines. So this is Jupiter, Saturn, Uranus, Jupiter, Saturn, Uranus, Neptune. Right? Yeah. Jupiter, Saturn, Uranus, and Neptune. And they have these curvy lines because this is the line of influence of that planet. Each planet has a line of influence. That basically means if an object is along this line, it crosses the orbit of that particular planet. And if you cross the orbit of the planet, you have a problem. You either hit the planet or you're kicked out by the planet. Now, the hitting of the planet, we have seen this Shoemaker-Levy 9 a decade ago, and the kicking out, we have done it ourselves with the Voyager spacecraft. So both can happen. Now, the most likely scenario is that asteroids which are born in the neighborhood of Jupiter and Saturn are kicked out along what I call here the conveyor belt. So they're kicked out very efficiently. But if the sun is in a star cluster, if asteroids are kicked out at a distance of about 1,000 AU, they're basically picked out by a star. They're kicked out of the solar system. We lose these asteroids. And the time scale on which Jupiter and Saturn kick out asteroids is less than 10 million years. So in 10 million years, you basically lose all the asteroids in the neighborhood of Jupiter and Saturn. So the sun was then still part of the star cluster. So we cannot explain the Oort clouds by kicking out asteroids by Jupiter and Saturn. But what is remaining is Uranus and Neptune. They do the same process but on a time scale of about 100 million years. So while Jupiter and Saturn kicking out the asteroids, the sun is being perturbed by another passing star. In the end, the sun is escaping the star cluster on a time scale of maybe 20, 30, 50 million years. And then Uranus and Neptune start kicking out these asteroids in the extremely elongated orbit. There's an eccentricity of 0.99999 until they reach almost the tidal boundary of the sun. By that time, the galactic potential. The interaction with the galactic potential circularizes the orbits of the asteroids by Nilo-Kozai cycles, and they become here part of the Oort. So the Oort cloud was made after the sun left the parent star cluster, and by kicking out asteroids due to Jupiter, due to Uranus and Saturn. At the same time, the sun has achieved a number of asteroids in what we call here the captured asteroid zone and the parking zone. The parking zone is still there. That's where you find Sedna. The ones that are in the captured asteroid region are brought into this conveyor belt machine and also become part of the Oort clouds. So the Oort cloud is composed of original material between Uranus and Neptune and from a few asteroids being captured by other stars in the parent star cluster. Now, how does it look like? It looks as follows. I have a little animation for that. Let me, well, we're in Zoom. That's not really complicated animation. So this is an animation you can also see on YouTube. The asteroid is launched between Jupiter and Saturn. It's kicked around by the planets, and at some point it's being kicked out in more and more elongated orbits. As we can see here, they get more and more elongated in time. And in about 1 million years, they immediately reach something like the Oort cloud, where they get circularized. And the circularization process itself is a random walking phase. So if an asteroid, as soon as an asteroid is kicked from a very high eccentricity orbit, the eccentricity into a semi-major axis of something like 10 to the 4 to 10 to the 5 AU, it will circularize in sort of a random walk. So the color coding here is time, where red is the latest. And it takes about 100 billion years to circularize the asteroids. So in the end, the Oort cloud will have a density distribution looks a bit like this. You have this is in log A first 1 minus eccentricity, because for theories sometimes it's easy to think in these terms. These lines become straight lines. Asteroids are kicked along this conveyor belt into the regime where they're perturbed by the galactic tidal field and the galactic potential, and then they circularize and become the Oort cloud. So this is the Oort cloud here. And then, of course, this all happens in the galaxy. So the sun is part of the galaxy, the star cluster is part of the galaxy, the stars that the sun was born with are all around us because they stay in the same orbit, more or less. But also the asteroids being kicked out by the planetary system are sort of in a banana orbit in front of and at the back of the sun. So the asteroids we lost are still around. We didn't lose them really. It is like lost family. It first goes to the, it's like astronomy like. You finish your PhD, you go to Japan, and then in the end you go back, and instead of living in Amsterdam, living in Ireland, right? You go to Heidelberg, you're born in Heidelberg, you die in Munich, right? That is sort of what happens to these asteroids. They all stick around, it's all family. It's not really a very good family because they all go away a little bit, but not too far, at least most of them. So the third interim conclusions, the Oort cloud did not form in a simple process. It's really a combination of processes we need. It evaporates in the galactic tidal field on a time scale of about 2 gigayears. The material lost from the solar system stays in the parent orbit. That's not only for the sun, but it's for all stars in the galaxy the case. And the lost objects, Abiomua may be very well such an object, not from the solar system, but from another star being kicked out. So in the end, being born in a cluster has long-lasting consequences for the planetary system. There are aspects of the solar system which you can relate to what happens very, very, very long time ago. You just solar system is just like you. If you're traumatized at youth, you're still in trauma, and the solar system still has a trauma of its youth. Many of these processes operate in clustered environments. Most of these perturbations are initiated in the cluster, either when we still had a gaseous disk, or when the disk was already solidified into chunks, into asteroids and planets and comets, etc. And the Oort cloud was only formed sort of in this process. So the challenge, I think, is can we recognize these processes? Can we look at the planetary system and say, hey, you had a trauma in your past, something happened, and we think that that star is responsible for kicking out your nice planet. That's my story. Thank you.
Thanks, Simon, for this great story. I think we all enjoyed it, and it's amazing what we can learn from anybody that reads about hydrodynamics, about the solar system, about many aspects of what is common in DC communities. So there are many questions.
To include some of the results in one of my works, there's still one thing that makes me a little bit unsatisfied, and the argument comes from geophysics. For example, in the last 4 or 5 billion years, there might have also been some supernova in the vicinity of the sun that increased the metallicity of the sun. They could have changed also the Oort cloud and the translation of the solar system. So there are several elements that might have been younger than just looking at the very early conditions.
It's more like a remark on a question, but I think the question is, how do I respond? I completely agree that I'm sure there are supernovae that have been occurring in the neighborhood of the sun in the last billion years, in the last 100 billion years, even maybe in the last 10 of millions of years. There are evidence for that in the sediment of the ocean floors, for example. But if you look at the effect of the impact of a supernova blast wave in the current solar system, it is extremely small. So what you can see is the accretion of material onto the planetary surface, or captured by the atmosphere, basically. That is a very likely possibility. But if you look at the stability of the Oort clouds, it's very hard to perturb the Oort cloud just by a supernova blast. If that happens, it really must have happened very close. And then I'm talking about within something like a parsec. And I don't think that any supernova happened within a parsec in the last 100 million years or billion years. Yeah, but even then, I mean, the average time of supernova in the galaxy is about 100 years. So calculate the probability of having one within a, let's say, 2 parsec or so of the sun. Really, it's still a very small number, I think.
Thank you, Bert. I had a question. The Oort stars, you mentioned there was time without the existence of the Oort star. Do we observe structures like the Oort star at similar stars like the sun?
So the question is, I shortened the question, right? The question is, do you see structures like the Oort cloud around other stars than the sun? Yeah, around other stars similar to the sun. Well, we don't even see the Oort cloud around our own sun. It's a completely hypothetical cloud of objects. And the only reason we know it's there is because of the comets. And the comets are things that came from the Oort cloud a long time ago and had, for some reason, a very elongated orbit, shoving it inside the solar system. And then suddenly you see it when it gets close to the sun, it starts evaporating. This is the night tails of the comet. So from other stars, we do not see anything like Oort clouds. We hardly see planets around other stars. That's already very difficult, right? And no asteroids. So
very nice talk. I have a question about supernova enriching the disk. Right? You say, well, it's very hard to enrich something with very tenuous gas hitting a very dense disk. But if the gas is so tenuous, maybe the question would be: is the gas cold enough that it would actually have dust grains in it? And if the answer is yes, dust grains actually does not get deflected, essentially like bullets, and then get stuck with this.
yeah, so the question for the people at home, right? The question is, if the supernova has a tenuous wind, let's say, the outflow of the supernova, but if the temperature is low enough to get dust formation, and the dust may be the thing that hits actually the surface elements, and that may affect, maybe stick to the disk because that's much more interactive. I think the answer is yes. I think that may happen. Yeah, I don't know if it happens at the short distance I have been discussing here, but this has been discussed also in literature that people calculate the dust contents in the supernova blast wave and what fraction would stick to the early solar system. And then I think, but I'm not sure, I think then you get into an overabundance of iron if that happens. Right? It's very easy to overabundance iron once you start playing around with supernova.
It's certainly true.
Are the inclinations of the comet orbits coming from the Oort cloud, which are usually assumed to be randomly distributed, consistent with your hypothesis of Oort cloud orbit? Yes. Very easy answer. Yes, they are. I have to say, so there's a caveat, and that is that the time scale on which the orbits of the Oort cloud object which came from the inner solar system circularizes is more than 100 million years. It's sometimes depending on the orbit, so it depends on the distance from the star. The closer you are to the tidal radius of the solar system, the quicker the process is, and the shorter in you are, it takes longer. And at some point, we stop the calculation because I don't have patience. So I stop at 1 million years, and then the Oort cloud objects within 10,000 to something like 60,000 AU were not all circularized. It's not isotropic yet. So getting the isotropic distribution may take longer.
While we get to further questions, I was wondering about Sedna. I was not aware that it probably has been captured by other things. And
well, it's not the only explanation.
I was also interested in the prospects of kicking out other planets and minor planets and so on. So there should be many floating around. What about lensing constraints on these things? Is this something that could be a potential constraint to your model, or is this just the way?
I don't know. So first of all, the model I presented here for Sedna, there is another model by Warren Brown who says there is an extra planet in the solar system, and that explains the growth of Sedna. So there are alternatives. I like this model, but then he likes his model. sociology of science. But your question is,
so there's all these free floating stuff, and you have lensing constraints.
Yeah,
And you
yeah.
have micro lensing service. And I was wondering whether you could use it to constrain it.
I'm not sure, but I should talk to the lensing people to figure this out. But I think they're not sensitive to objects as low in mass as 10 to the 21, 10 to the 22 solar kilograms. So I think the mass is too low of these objects to also Oumuamua, right? You know, it's just a rock. Yeah, yeah. So there are constraints from micro lensing on free floating planets, but I think they're under producing what we find in our simulations by something like the order of magnitude. So I think they should find more, and they think we should produce less.
So the motivation for investigating this truncation with the supernova blast work is, you know, in the solar system as an aluminum, which probably came from supernova blast. But you know, protostellar multiplicity is much higher in the early stages. So is it also likely that there's also this could be truncated by stellar flight rise early on as opposed to supernova blast phase?
Yeah, yeah. So I think if I translate the question is, or repeat the question is, can you make a distinction between if the protosolar disk was truncated by a supernova or by dynamic encounters? And I don't know. I like the arguments that the supernova tilts the disk. I mean, it is a very clear physical process that just operates. It's just how the hydrodynamics works. So the tilt of the disk, I like an explanation. Also for that, there are other people who have different explanation. Also there, an extra planet would help. Whatever you think of extra planets in the solar system. The enrichment is, I think, more due to Wolf-Rayet stars than to supernovae. So maybe if you could think of a situation where you have no supernova at all, but you do have the Wolf-Rayet stars. For example, if you're born in a more open star cluster where the Wolf-Rayet stars are floating around, but then the sun is kicked out anyway and the whole thing dissolves, so there's never a supernova in the neighborhood, then you have no choice than to do it by the truncation. And otherwise, I don't know. An extra indicator would be nice.
Let us thank Simon again for this super exciting